Okay, so we're going to be doing 2.6. We're talking about rational functions. So far, we've talked about polynomials, right? And we can graph polynomials. We can get zeros of polynomials. We can hopefully look at pictures of graphs and get the polynomial, and then vice versa. I give you a polynomial, you can sketch the graph. So hopefully we can do all those things. Now we're going to just finish up on rational functions. So let's define what a rational function is that we're going to be talking about. So rational function looks like this. It's going to be in the form of this. Some function, well, where'd it go? Whoa, isn't that weird? Hey, let's go over here. Oh, am I eraser mode or something? Whoa, there it is. There it all is. I don't know what's up with that. Okay, there we go. It's some function f of x equals p of x over q of x. So what I'm doing right now is I'm giving you the general form. So what does this mean? Well, this means that a rational function is going to be a polynomial over a polynomial. So when we take two different polynomials, such as p of x and q of x, when we divide them, we create something that's called a rational function. So I'll give you an example of a rational function right now. Here is one that we could all look at and take a look. X squared plus 7x plus 5. That's a polynomial, right? Its degree is 2. It's a quadratic, no big deal. As soon as I then divide this by, I don't know, x, and then x plus 3, and then times an x minus 4, I now have created a rational function. This top part is representative of the p of x, and this bottom part, the denominator, is representative of the q of x. Does that make sense so far? What a rational function is? You guys on board with that? Alright, now, the very first thing that we talk about when we talk about rational functions is their domains. And it's very, very simple to find. The domain for any rational function is going to be wherever q of x, which is the denominator, is equal to 0. And what we're going to do is we're going to exclude all of those points. So, as an example, for me and mine right here, in this case, do you see, can you think of a value that when you plug in for x in the denominator, it would create a 0? Lauren, give me one. Yes, 0 is one of them. Give me another one. -3, give me another one. 4. So we're going to use set notation and say that our domain for every rational function is going to use set notation. In this particular example, the domain would be all real numbers x, such that x does not equal 0, -3, or 4. And the reason this is the domain is because if we plugged in a 0, we'd get a 0 in the bottom, and we cannot divide by 0. If we plugged in a -3, it would make that middle term a 0, and would make it a 0 in the bottom. And likewise for the 4. Does that make sense so far? Okay. Let's do some examples. What we're going to do is we're going to find the domain for each rational function. We have 3 examples, and you can try one on your own down below. Alright, so we'll do A. And A says f of x is x squared minus 9 over an x minus 3. So what you want to do is you want to factor each term, the p of x. This is representative of the p of x, and this is representative of the q of x. If we factor everything, here's what we'd get. The top is the difference of two squares, so it'd be x plus 3 times x minus 3. And then the denominator is already factored into an x minus 3. So a lot of students want to just do this. They want to cross that out with that green line there. And technically, yes, you can. They do make a multiple of 1, so you can multiply by 1. But then, by doing so, you would be saying the domain then is everything, because then you're just left with an x plus 3, and that's a line. So, for the sake of finding the domains, I'm going to recommend that you don't do that. So the domain for this one is going to be all real numbers x, such that x cannot be 3. Alright? And the reason is because you have to revert back to the original rational function. So even though you can factor and cancel because there is a product of 1, you have to apply it to the original function given. So in this case, it would be all real numbers such that x is not equal to 3. Okay? Let's take a look at B. Right? I have x over x squared minus 4. So I would have x over, I'd factor everything. This again is the difference of two squares, so x plus 2 times x minus 2. So the domain would be all real numbers x, such that x is not equal to 2 or -2. And then, of course, we'd keep it in set notation. This making sense to you guys? You guys on board? Yeah, questions so far? Yeah. All right. This last one though, take a look at this one, and then we can stop for questions. We have, if I factor everything, I have an x plus 3. Can I factor an x squared plus 9 over in the real number system? No, because everything's positive, right? Well, this is just x squared plus 9. It does factor in the complex, but for us, our domain in this case would just be all real numbers. Okay, you and a partner try these, a and b. I've given you two rational functions, x squared minus 25 over x minus 5, and then x over x squared minus 16. I would just want you to write the domain in set notation. So everybody get those two answers? So everything except for 5 in the first one, everything except for plus or minus 4 in the second one there. Okay, we are going to now have a little discussion about the parent graphs of rational functions, and in particular, we're going to take a look at these two functions very, very closely. Okay, the first one is going to be 1 over x, and I've given you the graph. It's right here, so I'm going to highlight this one. We're going to talk about this function, 1 over x, and then we're also going to talk about 1 over x squared, this function over here. All right, these two functions, let's have a little conversation about them. Okay, let's start over here on 1 over x. I call this graph, this is the reciprocal function, because it's 1 over something. So it's the reciprocal function, but I call it the Hurley graph because it kind of looks like the Hurley logo, right? You can see that? And then the one over here, the one on the right, this is the reciprocal squared function, 1 over x squared. I call that the tree trunk for obvious reasons, okay? Because it looks just like a tree trunk if you do that, right? There it is, okay? Okay, the one on the left here, the reciprocal function, we need to know a couple of points. The points that we need to know are 1, 1, and -1, -1. So I would expect you to know that those 2 points are on the reciprocal function. How am I getting those? What am I doing? If I plug in x equals 1 to the function, what would I get? 1 over 1 is 1, so the output should be 1, right? If I plug in a 2, I would get 1/2. So notice 2, 1/2 is on there. If I plugged in a 3, I get 1/3. Notice 3, 1/3 is on there. You guys see that? If I plugged in -1, I would have -1. If I plugged in -2, I'd have -1/2, and so on and so forth. So by doing so, you create this sort of Hurley-looking function, right? There's also two very important things going on here, and I hope that you see them. One, there's something interesting that's happening right here. Do you guys see that? And two, there's something interesting that's happening right here. Do you guys see these two lines here? You may know what they're called? Asymptotes. Yes, they're called asymptotes. So let's write that in, okay? Okay, these are called asymptotes. There are two of them there. There's a vertical asymptote, and then there's a horizontal asymptote. All right? So we're going to talk more about asymptotes in just a second, right? Let's take a look at the 1 over x squared function. This also has some points of interest that we need to make sure we have, namely -1, 1, and 1, 1. So notice that those 2 points are easily defined, right? Then to get the other points, you simply plug in to the function, right? If x is 2, then the output would be 1/4. If it's -2, it's still 1/4. So we notice that we get all these points if you plug them into our function. Again, just like the reciprocal function, there is definitely something going on here, and you should take note of what that is. We're going to talk about that in a second. And then there's also something going on right here. So both of these functions have asymptotes, right? Okay, and let's talk about what you know about asymptotes. There's one there, and then there's one there. What do you guys know about asymptotes? Yeah, everybody always says it's this function, it's this graph, this line that the graph never touches, okay? And that's only part of the story, all right? So let me give you the actual true definition of an asymptote, all right? So an asymptote, so this is, you don't need to write it down, but I want you to understand what it truly is, right? An asymptote is a line, so I have like the green one there or the purple one there for both my graphs. It's a line that your function behaves like for very, very small values of x and very, very large values of x. Now that doesn't make a whole lot of sense when you hear it once, but when you hear it 3 or 4 times, it makes a whole lot of sense. Notice that definition has nothing to say about can never cross, because I will show you an asymptote where the graph actually does cross, okay? When you're young little people and you're learning about math, and they say an asymptote is a line that doesn't cross, and that gets you as far as you need to go at that moment in time. But we're bigger people now, And so I'm going to give you a more sophisticated definition of an asymptote. And I'll say it again. It's a line your function behaves like for very, very small values of x and very, very large values of x. Okay? So to explore that idea a little bit more, check this out. Here's the graph of 1 over x squared, right? And if I zoom in like this and I go ahead and I put my asymptote in, my asymptote is right here, right? Okay, so for very, very small values of x, I'm talking about values of x that are really, really tiny, like 0.001. So if I zoom in to like point as far as I can go, right? And I go all the way up the graph. And remember, my asymptote is still right here, right? You guys see that? So the farther up I go for very, very, very tiny, tiny values of x, notice what's happening to my graph. It's getting closer and closer and closer to that line, right? So it doesn't ever touch it. No, it gets closer and closer to it. So the true definition for us is a line that my graph behaves like for small and large values of x. Around medium values of x, it can actually cross. Very interesting, okay? So we're going to be talking about these asymptotes, and they're going to play a role in what we're doing. All right, so how do we use asymptotes to talk about graphs of functions, okay? I want to point out something, that this graph that you see here, the parent graph would be f of x would be 1 over x, right? If I was going to graph that one, there would be a point there, there'd be a point there, I'd have an asymptote here, and I'd have an asymptote down like that, right? So, and the asymptote would be, the vertical asymptote would be here. So how do you think I went from the black graph to the red graph? What does it look like to you? It's like I moved it where? 2 units to the left, right? Oh, check it out. There's that point and that point. I wonder how I could use this function and translate it. What would it be? It would be f of x would be 1 over x plus 2. Very good. And notice the x plus 2 is in the denominator, right? Because if it was outside the 1 over x and then a plus 2, the whole graph would be moved up 2. Okay? So I'm going to erase that now. So now we actually have this graph to work with. Okay, and this is f of x equals 1 over x plus 2, all in the denominator. So I'll erase these things on the side. Okay, so that means I have a vertical asymptote here, right? And what's the domain of this rational function? You guys can tell me what that is. What would it be? All real numbers. X such that x is not equal to what? Negative 2. Are you guys noticing something? There's a connection between the domain and vertical asymptotes? Interesting. Yeah. Okay, good. That's coming up in box 6. But what I want to talk about now is this arrow notation, all right? So here's arrow notation. And it looks like this. And we're going to say, as x values approach negative 2. Okay, this is the beginning of like how to use limit notation and calculus notation. So as x approaches negative 2, so what do I mean by that? Well, I mean that as you're traveling on the x-axis toward the value negative 2, we're going to describe how our function is doing. F of x is doing what? That's what we're trying to get at. Well, do you notice that there's 2 directions that you could, if you're standing on the x-axis, there's 2 directions you could approach 2 from. You can approach from the right, or you could approach from the left. Do you guys see that? See the 2 arrows I have? So we have to have a way of talking about arrow notation. So what we're going to do is, if we are approaching a value from the right, we put a little plus sign above that. Okay? So as we approach negative 2 from the right, so as I'm approaching negative 2 from the right, what's going on with my function? Where does my function shoot off to? Where does it go? It goes up, right? So if I move from this point to this point, I've gone from there to there. Do you guys see that? And if I move from this point to this point, I've gone from here to here. So as x goes to negative 2 from the right, where does our function go? Oh, there's a place. What's that place called? It's called infinity. It goes to infinity. Right? So the closer and closer I get to negative 2, the bigger and bigger my function gets. Okay, so this is called arrow notation. We are describing as we're getting close to some value of x, our function does something. Alright, well, let's approach it the other way. I'll give you a different color here. We'll go orange. So as x approaches negative 2 from the left, and there would be a minus sign there. So as I approach to the left, where does my function go? It goes to a different place. Where is it? F of x approaches negative infinity, not an 8, negative infinity. Okay? Alright, I have another one for you that I want you to try. We'll do it together. Okay? Let's take a look at this one. And I gave you this one because, look, there's an asymptote here. Check it out. There's an asymptote. It's a horizontal asymptote. And look what happens. The graph actually does what, you guys? The graph crosses it. So there's a horizontal asymptote there, which we're going to discuss more about. So that's why I wanted to give you that more sophisticated definition. Okay, let's go to 100%. Alright, and there's also two vertical asymptotes. Do you see them? There's one here, and there's one here. Okay, so here we go. So as x approaches 4 from the right. Okay, so here is 4, and as I approach from the right, where does my function go, you guys? It goes to a place. As I approach 4 from the right, my function goes to infinity. Very good. As x approaches 4 from the left, where does my function go? Negative infinity. F of x goes to negative infinity. Dang, why do I keep doing 8? Sorry. Negative infinity, right? Okay, take a look at this one here. How about as this one? As x approaches negative 4 from the right. As we approach the value of negative 4 from the right, where's my function go? F of x approaches positive infinity. Good. How about as x approaches negative 4 from the left? Where's my function go? Negative infinity. Good. Okay, let's give you a different one here. How about as x approaches 1? Ooh. As x approaches 1 from the left, where does the function look like it goes? F of x goes to the number 1. It stays right there. Do you see it? Yeah. Okay, what about as x approaches 1 from the right? It still stays there, right? So f of x approaches 1. So it doesn't always have to be an infinity. That's the whole point I'm trying to make. It doesn't have to be an infinity. Okay? You guys cool with that? Alright, great. Okay, so I'm going to show you how to find a vertical asymptote and then give you an example. You already know the answer to this because we just alluded to it about 5 seconds ago. So if I give you any general rational function, like p of x over q of x, so if you're given a rational function, to find the vertical asymptote, you set q of x equal to 0 and you solve. So basically you set the denominator equal to 0 and you solve, because that's where you're going to get errors in your domain, so that means there's a vertical asymptote on the graph. So you set q of x equal to 0 and you solve. So last and final box here, if I asked you to find the vertical asymptote and make a quick little sketch, what would we do? Well, first we would factor this thing into x plus 3 and x minus 3. That's what we would do first, right? Then we would set q of x equal to 0 and we would solve. Well, we'd get x plus 3 times x minus 3, and we'd set that equal to 0. Should be implies. So therefore I can see right away that x is either going to be negative 3 or x is going to be positive 3. So this right here tells me exactly where the vertical asymptotes will be. So if I was going to make a little quick sketch, my graph would look something like this. I know I'd go 1, 2, 3. There would be a vertical asymptote here. And 1, 2, 3, there would be another vertical asymptote here. And then there'd be some stuff going on in between, but I don't need to concern myself with this particular lesson. That's for the next lesson. Okay? So you're going to be asked tonight to solve or to determine where are the vertical asymptotes, right? What you're doing is you're examining where the denominator of your rational function is 0.